Hello everyone. In this video we are going to solve wave equation as usual using finite difference technique. In this video we will see how we can apply Neumann boundary condition, as some of you asked in the comments about the applying of a Neumann boundary condition. So in this video you can find information about it. And if this is the first time that you are visiting my channel, if you are interested to such stuff, don't forget to subscribe my channel and like the video, and if you have any question, don't hesitate to ask in the comments. So let's start. Okay, as you know, this is the general form of wave equation. Here t is time and x is coordinate, c is velocity, and f is source term. In order to have unique solution, we should have some initial conditions and boundary conditions. And what you see here, this is indeed the Neumann boundary conditions, right? And it say that in addition to the knowing of the value of function at the boundaries or at the zero moment, we should also know the first derivative of a function at the same boundary or at the initial moments. And here you see that this u0 x and u1x, they should be well known function in the interval of a to b. And here is the boundary conditions, and if we say that okay, our boundary limited to the a and the b, we should have a well-known function in whole of the time that represented with phi1 and phi2 when time is greater or equal to 0. If we want to simplify the problem, imagine that c is 1 if function is 0, a is 0, and b located at 1, also phi1 and phi2, they are 0, and the value of function at the initial moment and the derivative of function at the initial moment, as we mentioned that we defined with u1, they are both of them are sine pi x, right? So by applying this condition, this problem, this partial differential equation will be simplified like this. And if we write the initial and boundary conditions here, we say that okay, at the zero moment and at every point on the x, and also moreover derivative of function with respect to the t at all position and at the zero moment, they both are sine pi x, and at each time and the left boundary that are located at 0, the value of function at this boundaries is 0. Moreover, at the right boundary, the value of function is 0. And as you know, by using of a finite difference method for solving of a partial differential equation, the first thing that we should do is discretizing of the domain. And here you see the x and time axis and the discretized domain here. And if we apply the definition of a finite difference technique for this PDE, we will have something like this. Here we assign index j for the t-axis, and we assign index I for the x-axis, right? And using the definition, we should have something like this. And what we need is this value, because j represent the time, and we are interested to find the value of function at the next time step. We just multiple both sides of equation to the delta t squared, and by defining of delta t squared divided by delta x squared by a factor s, we can simplify the function like you see here. As I mentioned, it's enough to just keep this value at the left and gather all the other at the right. And if we do that, we got to such a equation. And I think if you look at this equation, you will understand that why we need here Neumann boundary condition. Imagine that J0 represent not J0, J1. J1 represent the initial moment. If we substitute 1 instead of j, we will have ui0, ui1, and all of this will be ui1, ui minus 1, and 1, and the right part will be ui2. What does it mean? It means that we know the value of function here with uj, and also from the derivative of from the first derivative, we know the value of function at this position, and we should start finding the value of function from this position. I mean that we know all the value of function at this position and also at this position because of knowing of the having of the Neumann boundary conditions. Right, and what else we need? As we mentioned, we should know the value of the first derivative with respect to the t, and we say that this is u1. But again, using of the definition of finite difference technique, we can say that instead of first derivative, we can write uij plus 1 minus uij divided by delta t, and this is function u1. And we can find the value of this uij plus 1 according to the u1, delta t, and uij. And if we say that a0 here represents the initial moment, and we substitute 0 here, what we have is ui1 equal to u1 delta t plus ui naught, right? And we know this function. This is indeed the value of function at the initial moment, value of function here, and we know that this is sine pi x. Moreover, we know this function, and we say that okay, this is well defined, and this is again sine pi x. And if we substitute sine pi x and take the factor out, this sine pi x, what we have is sine pi x multiple to the 1 plus delta t. And as I mentioned, we mentioned that we say that the value of function at the initial moment is sine pi x. I boxed this to function here because we will need in writing out the code. And I don't solve this problem analytically, but I think this is easy if to check that this is the solution with the mentioned boundary and initial moment. For example, if you substitute t equal to 0, what you got is sine pi x that we mentioned. Also, if you take the derivative of this function and substitute again 0 instead of substitute 0 instead of t, you again will find sine pi x, and this analytical solution satisfies our partial differential equation with aforementioned boundary condition, initial and boundary condition. I think this is enough for the theory, and I want to start writing out the code. So let me pause here. Okay, I open the MATLAB and I start new script. As usual, I will start with CLC, clear and close all. What we need, okay, number of gradient x with nx if, okay, let it be 10. And number of grid in the t direction, let it be, for example, 30, right? What else? A. Okay, A is 0 and B is 1. T0 initial time is 0 and the final time TF, let it be 2, or what else, 1. Okay. Therefore, what will be x? It should be b minus a divided by nx minus 1. This is dx, and dt will be, it should be not 1, b minus a, okay, it will be t final minus t naught divided by nt minus 1. Therefore, x should change from a with a step of dx to b, and t should change from t naught with the steps dt to tf, right? What else? Let's define factor s here, and this is the t squared divided by dx squared. Okay, Let's start from an analytical solution, right? So, analytical solution. As usual, if you saw my previous video, you know that how I find the analytical solution, usually inside the loop for I from 1 to nx, and another for sweeping out time from k from 1 to nt, right? And okay, and what is our analytical solution? I define it with u a I j, and as we said, it should be sine pi x. So okay, sine pi multiple to the xi multiple to the cosine pi t, pi multiple to the t j, okay, plus sine pi multiple to the t tj, pi tj divided by pi, right? And before that, let's allocate some memory to the analytical solution. U a should be zeros, and nx and x and nt, right? Okay, semicolon here, and let's plot it with contour f, contour f, okay, contour f, okay, I think this is correct. Contour f ua about the color of line, it should be line of color none. Let me check, I forgot these commands. Okay, line color, it should be 9, and this is number of okay, let me copy it from here. Let me copy all. Here is figure, Control C, Control V. Okay, we just here define the figure 1, and using the command contour of if we want to plot the analytical solution. Here 200 represent the number of line that we want to use in the contour plotting, and the line of the color we defined here we don't need any color, so we write here none. Title is analytical solution, X label is T, and Y label is X, and color map, we need to see the color map, and no, here color bar in that will appear, this command will appear the color bar, and the family that we are using for color map is jet family, and this number represents the number of color that we want to use. I think if you look at previous video, you should know all of this. By the way, let me save this. Let me save this program. Okay, wave equation 2. Save, and let's check, is it fine or not? I press F5. Okay, and here you'll see the analytical solution of wave equation. And you see that indeed here is x, and here is in time. If we increased, for example, the maximum time to, for example, 10, let's see, you can see more wavelengths inside in this time interval, right? And you see here the quality is not very good because we can increase the quality just by increasing our number of grid. 100 and 300. Press F5 one more time. Okay, you see. Okay, for simplicity, let's start with a small number of grid. 10 and 13. Okay. And ND, DT, T, I think everything is okay. And here we want to numerical solution, right? Again, similar to the analytical, let's assign a memory for this numerical solution, and we define it UN. Okay, UN again is zeros, NX, NT. I just copy it from here and paste it here, right? Okay, then what we need a boundary initial. Look here, because we defined a zero matrix for all the domain. Here by default our boundary condition satisfied, because we say that at the left and right boundary the value of function is 0. So this definition of this UN by zero matrix satisfy the boundary condition. What we need is initial condition. So initial condition at every position and at the 0 moment, represented with index 1, because in MATLAB we cannot assign index 0 for the matrix. The sign pi x, right? Sign pi x. What else? We find out that if we refer to the slides here, also we have such a conditions for this position. It means that in the second grid, in the one grid after the initial grid, we have sin pi x multiple to the 1 plus delta t. So UN at all position, and this in the second, it should be sin pi x, pi multiple to the x multiple to the 1 plus dt. And this is true only if our dt tends to 0, because this is we know that in definition of a finite difference we should have a small interval in both time direction and in space direction, or what other variable. Interval should be small. And again, using the two loops for I changes from I think it should change from 2 to nx and j should be changed from 2 nt and for I, why it doesn't work, I don't understand. Here we have 2, 4, I forgot the 4, okay. And what else? Here, let's look at the equation that we derive. This one, okay, uij plus 1. U and I j plus 1 is equal to what? S multiple to the S multiple to the U numerical I minus 1 j, right, minus 2 U numerical, I forgot the are here, U I j plus ui plus 1j. Copy it here and paste here. U I plus 1j. What else? I think here it should be plus 2uij to multiple to the un ij and minus uij minus 1. This is not minus, this is plus, and this one is minus, and Control C, Control V, uij minus 1. Okay, if let's check it for let's check it just okay, if we substitute 2 instead of I, we will have 2 here, 2 here, and 1 here. Okay, so we have the first one, we have the first index, and if we substitute 2 here, we will start from the third. As I mentioned, we should start calculation from here, and this is the third grid. If you count 1, 2, 3, right? This is 1, this one is 2, and this one is 3. And when we start from 2, by default, we will calculate the third grid. And here we will have the 2 minus 1 is 1, first grid, 2 second grid, second grid, second, and third grid here, right? I think everything's correct. Just let me check. And here it should be minus 1 and minus 1 here, because the maximum index is nx, and when we put nx here, or nt here, we will have some nt plus 1 that is out of the dimension of our matrix. So, and just I think we should note here, because this is an array, this is not a scalar, this is an array. What else? I think nothing, and everything is correct. And I just copy it from here again. Control C. Control V, and here is numerical solution. Numerical solution, and the recording. Yes, I'm recording. Okay, I think everything is okay. Let's run it one more time and see the numerical solution. Oh, look at numerical solution. Terrifying. Okay, let me check what we have here. Here, guys, I had a mistake here. Be careful. When you calculate the PDE numerically, you should be careful, because we find the value of function at the next time step. So first we should calculate all the value at all x. I mean that first you should calculate all of this point, then this point, then this point. So you should, the first loop should be devoted to the I, not j. I start from j here, so I should start from I. I just cut it from here and copy here, and cut it from here and copy here. Now when I calculate the position for each time, I calculate like this. But if it was like previous, it was like this. Calculate this, then this, then this, then this, and it will cause a great error that you see here. And if I replace, let's run it one more time. As you see, this is the numerical solution, and this is analytical solution. And let's calculate the error. So here, error, okay, and I defined it with E, and this is nothing, but let's look at the absolute of the error. U analytical minus U numerical, and let me copy it again from here, and it should be error and error, right? Let's run it one more time. Oh, I didn't put semicolon here. One more time. And you see error is in the order of 0.035. And if we want to reduce the error, I think we should increase the number of grid in both in X direction. I think if we increase the number of grid in X direction, put it 100 and calculate it one more time, and you see that error decreased to 0.01. And here is numerical, and here is analytical, and here is the error. Where is it? This one is the error. And I want to show you something. It's about the factor s, right? I want to show that when the factor s is greater than 1, you will have extremely big error. In order to that, let me put the final by 1 and put 100 both for both X direction and one direction. Number of grid in both direction is 1. And now you see that s is 1 here, and error is acceptable, 0.15, right? Error is now is acceptable. What if I increase this s slightly greater than 1, just by increasing our nx by 101? Let's see. This is 1.02. S is 1.02. Sorry. Okay. I think this is not very sensitive. Just slightly more. 102. 1.04. Now you see when this is greater than this, when it's slightly greater than 1, you see how much error is increased. And if I increase s more and more by increasing, for example, nx or reduction nt, no matter, for example, 110. You see s here is 1.2. You see this is completely wrong answer. There is not true answer for the numerical solution. Therefore, in a calculation of wave equation, you should be careful about this s factor. This is known as Courant number. So, in wave equation, Courant number should be equal or less than 1. And if you want to decrease the error, you can reduce it more by increasing, for example, nt to 1000, and let me increase it to, for example, 3. This is 0.88. Let's see how much will be the error. You see error reduced more in the order of 10 to minus 3. Right? Analytical, numerical, and the error. What if I increase it more, 2000? So 0.22. Courant number is 0.022, and let's see, it's calculating. You see the error decreases slightly. It was 5, the maximum was 5, now it's 2.6 or 7, something like that. And if you want to calculate for further time, you can increase the final time by 10. But here you see the Courant number increased to 0.24. I think the error should increase at the further time. Let's see, because Courant number increased. You see it's slightly increased, but again it's in the order of 10 to minus 3. And as you see here is numerical, analytical, and this one is error. I think that's it for today. If you have any question, don't hesitate to ask in the comments. Thank you very much, and bye bye.